great pleasure to be here. I'm going to start with an apology. And the apology is because what I'm going to show you in the first few slides, you actually know already. But it's worthwhile reminding people of some of these things. If the machine will work. Yeah. We live in a very complicated system in which all the different bits interact with each other. And the trouble is that human beings have really got into this and have progressively increased in number so that they impact on all of things. And when we look at the problem of mitigating the effect of one of these impacts on the other, you've actually got to look at the consequences for all of the other elements. And of course, most recently, we've really become very seriously aware of the effect of greenhouse gases on the climate. Now, if we look at the, if you like, the main pollutant in this system, it really has to be people. And this slide simply shows you the utterly dramatic way in which the human population has exploded in the last couple of centuries. And we talk of explosions, population explosions in fossil groups. There's probably never been anything quite as fast and dramatic as this. And one of the points I'm going to make is that really all the problems about which we should be talking really scale as the number of people. Take, for example, the irrigated area on the surface of the Earth. Plotted on one side here, you've got the irrigated area in thousands of kilometers squared. That's the yellow curve. You've got population here, that's the boundary. And you can see one just rises with the other. And indeed, given that 70% of the world's water is actually used for irrigation, you can see that we're headed into a difficult direction, not just short of land, but potentially short of water in many places as well. And if we look at the energy scene too, as you might expect, as the number of people rises, so does the per capita energy. With a few hiccups, obviously here and there, but it's a pretty good correlation with amount of energy plotted horizontally there. And if that's what happens to energy, as you might reasonably expect, this is what happens to emissions too. Population again vertically, amount of the concentration of CO2 in the atmosphere plotted horizontally. So, in general, if we are looking at the situation, the globe today, it's actually people that we really need to be concerned about. And although it really becomes quite a different talk, probably in addition to the other things that we'll be talking about later on, we do need to be thinking about education for women in the developing world. Now, water and energy really go together pretty closely. More closely, in fact, than many people realize. And water is indeed needed for most energy production, and indeed for carbon capture and storage, which we expect to play an important part. And it's also needed for water production, and indeed in many cases it is in fact the largest cost in the production of water, pumping it or pumping it, or what have you. And there's a sort of useless factoid. Per capita, globally, we use about 1,000 times more water per head than we do oil. And, intriguingly, we are prepared to pay approximately 1,000th per unit volume that you do for oil. But this has various consequences, and one is that, of course, oil is transported long distances, but water tends not to be. And in general, people move to water, but on the other hand, oil is moved to people. And the thing you have to recognize is that ultimately, if you've got enough energy, and you can, or particularly cheap energy, you can produce water, because you can desalinate and you can transport the water. So in that sense, energy becomes fundamental and is really key. Now, let's switch now to a little bit more detail of the problem which has been concerning us and all sorts of, and others. Incidentally, I wonder whoever's looking after the clock could actually make it work, because it's still, according to the clock, it's still had 20 minutes, and that can't be quite right. We, again, plotted here vertically, you've got tons of CO2 in the atmosphere, and plotted horizontally, you've got years going from 2005 to 2035. And we've got here emissions. And coal, as you can see, is responsible, is the largest contributor to fossil fuel emissions. Only 20% of all energy, 28% of all energy, but 44% of fossil fuel emissions. Gas, 22% of all energy, but only 20% of emissions. And liquids, 33% of energy, 36% of emissions. Notice that these three here only add up to something 80+%, because of course we have energy from other either low carbon or effectively carbon-free sources as well. Now, really what we're concerned about is the rise of these emissions, and once we get into the red shaded area, we're into an area where there really are very serious consequences. So the question is, how do we get out of that most easily? Now, clearly, coal is something that we need to target. And if, for example, we could replace most of our coal with gas, that would probably bring us down to something like here by 2035. Now, replacing all of it by gas is unlikely to be practical. So if we can actually apply carbon capture and storage to both coal and gas, and separately do something about the liquids, we may be getting somewhere. So one way forward is to think about carbon capture and storage and the replacement of coal with gas. I mean, those are effectively trends that we should promote. But the other way of tackling this is to look at whether there are low-carbon alternatives to some of these fossil fuels that we've been looking at. But any alternative really has some big challenges to match. And the thing is that oil and gas are uniquely able to store energy in a small volume and release it quickly. And that really is a pretty remarkable and important property. They're both readily transportable, and coal is very easy to store, you just pile it up. And if the externalities, the environmental externalities, the costs associated with the use of fossil fuels are ignored, they're relatively cheap. And it is important to remember that they are actually used in two importantly different ways. And they're used in a static context and in a mobile context. And this really means that these can be tackled by quite different alternative fuels. So let's look for a moment at static fuel use. Basically here we're concerned with heating, cooling, all of the big industrial processes. And in this context, the weight and size of the engine, the characteristics of the fuel are not that important. It is important, of course, is it be low carbon and that it be readily available. And flexibility is the other important property because in particular, if you've got a significant amount of intermittent renewables in your mix, you really want to be able to back that up. And you need, in general, to be able to follow load. So you can look at a future mix, which is actually going to vary from country to country according to the politics in the country and according to the degree to which the country has good tides, has good wind, has good sunshine, and so on. But this is the sort of mix that you see: some nuclear, some intermittent renewables, hydro, wind, solar. You should put some geothermal in there. But you're going to need fossil fuels to effectively back this, deal with intermittency and inflexibility. We're going to see gas replacing coal, and we've got to have CCS. And the challenges associated with this are, first of all, getting the cost of CCS down. I don't think anyone in the CCS game has any doubts that it can be done at scale. The big question is, can the cost be got down to sufficiently low that it becomes globally applicable and useful? And of course, energy storage is, if you like, the ultimate goal, because if you have intermittent energy sources which produce energy in some cases at times when you don't want it, if you can store that and then call them at the times you do, you're really very much better off. So these are the challenges. Now, as another one, we talked about a little bit about gas and the possibility of replacing coal, and of course the whole fossil fuel game has been changed profoundly over the last decade or so by the recognition by the major energy companies of the importance of shale gas. Minor companies have been exploiting it for decades, but it's really come onto the scene in a big way in the last decade. And on this, we've got volume, or supposed volume of reserves, vertically here, and you've got the reserves associated with several different countries. Now, the orange columns here reflect the amounts suggested by BP in 2009 in their statistics. The grey columns represent information from that well-established geological journal, the Financial Times, and their estimate in 2011. I don't really believe any of this. I think there's still enormous uncertainty about the availability volumes of shale gas that may be there and their accessibility. But that said, almost certainly the world reserves of gas have in principle been increased by a very large factor. And I say that because really the one country where there has been significant shale gas exploration is the United States. And what we all know is that the geology and the geological history of the United States is not unique. There are many parts of the world which have similar geological histories. It would be very surprising if shale gas was not available in many of these as well. So, although the details of those great curves may be wrong, probably the principle is right. The other big thing about shale gas is that its distribution, geographic distribution, is very different from that of conventional gas, in which, so far the Middle East and the Russians have really had the field to themselves. And this much widening, this great widening of the availability of shale gas has considerable geopolitical significance for fairly obvious reasons. So what is the future going to be? Well, shale gas, gas emissions, as we saw before, are roughly half those of coal. And provided that two conditions are met, shale gas can be important. The first is that the environmental impact of exploration and exploitation of shale gas can be managed, and I think there's every reason to think that they can be. The other is the availability of water. And this may be, in certain parts of the world, the main limiting constraint of whether shale gas concentrations can be exploited. And it becomes attractive in general because gas-fired power stations are about half the cost to build of coal-fired power stations, and they can be flexible. So they really are appropriate for the kind of world we've been describing. And as I pointed out, traditional suppliers have been, or the availability of supplies have been widened. And indeed, if priced competitively, you may find both the displacement of coal on land, and you may find LNG probably used for shipping as well. And shipping is a major polluter at present. Although shale gas reserves globally, as I pointed out, are likely to be large, the effect on global prices is likely to be much less than has been expected by some. And this is because gas is the least transportable of the fossil fuels. It adds something over $3 to the cost of shale gas to move it round. You've got to compress it, you've got to put it in a rather specialized transportation vessel, and then you've got to have a decompression facility at the other end. It can all be done, but it means that exporting gas from a place where it's produced is quite an expensive business. And so the real benefits, the major benefits of shale gas are going to be experienced in the places where it is produced. And I think that it's going to give a massive boost to the US economy, and we may see that effect elsewhere. And the big question, we say, is whether it will be water limited. Now, if one turns now to the use of, or to what might be available to replace fossil fuels in the other area of transport, here the weight of the system becomes critical. And the essential combination is that you have a high energy density fuel coupled with a high power density engine. And of course, the internal combustion engine is just brilliant for this. Very, very difficult to replace. And today, we clearly have some alternative possibilities for vehicles. We know all about hybrids and electrically driven battery vehicles and so on. The trouble is that aviation looks at present as if it is going to be dependent on the internal combustion engine plus liquid fuels for some time to come. And so you say, well, what are the alternatives for liquid fuels for the internal combustion engine? Biofuels, but I'm calling here crop-based fuels, crop-based liquids. The difficulty with these is that the efficiency of use of sunlight by most plants is very low, around about 2%. Sugarcane, interestingly, which is probably the most attractive biofuel, has an unusually high efficiency of around about 8%. But this low general efficiency means that crop-based fuels cannot be a global solution, because the area that you need, the area of land area that you need, is just too large. The liquids, another source of liquids, is the organic waste. We human beings are very wasteful, and we produce an awful lot of organic waste. And there is a very high energy content in the organic material that we throw away, old tires, waste food, things of that kind. And indeed, the energy can be extracted from that. You can make gas, you can make liquids. But dealing with the heterogeneity of the waste we produce is chemically quite difficult, and there's a limitation there. We can also make, of course, liquids from natural gas, but actually that's a pretty dirty and energy-intensive process, and it's not something that you really want to do if your prime aim is actually to reduce emissions. And one of the most intriguing new technologies is the industrial production of bioliquids by photosynthesis, in which you don't grow the plants. What you do is simply grow the cells in the factory conditions. You feed them with light, a little bit of and some CO2 and things like that, and you produce your liquids directly. Now that's not developed on a large scale, but I think it's going to be something for the future. And then we just have to mention hydrogen. The bottom line on hydrogen is that you might make it from seawater with a microbial intermediary, or from nuclear, but you do need a safe and affordable bulk storage and transport system. And you might indeed get electrical power from the combustion of hydrogen in air. Beautiful. And you could use for transport, hydrogen fuel cells and so on. Great, well, we can do that already. But there are real problems. And in spite of the advances which are made, this still looks decades away. And I think that the challenges with generation, distribution and storage are such that we're going to have to do quite a number of other things in the meantime before we get to this, if this indeed is the way forward. So, to conclude, first of all, global emissions and all of other problems grow with the population and the per capita use of energy and water. And we have to think hard about population. I think water constraints are going to drive re-optimization of power generation. It's not been necessary in the past, but it's certainly going to be in the future. Shale gas will locally displace coal and reduce greenhouse emissions. It may not have a massive effect on global gas prices, but its effects will be significant. There's going to be a continuing need for high energy density liquids for transport, particularly air, but probably for some surface processes as well. We're going to need low carbon flexible generation to support inflexible intermittent sources. And there are alternative energy sources on the horizon, but no quick fixes. And the grand challenges are affordable carbon capture and storage and energy storage. All that said, we mustn't be too arrogant. If I look at the technological advances that have existed in my lifetime, they are truly astonishing. It was a long time after I graduated before anyone outside the physics community had heard of transistors. And transistors and printed circuits have simply transformed the way that we do all manner of things. So let us not be too arrogant and recognize that there may be technology surprises which we don't know about yet and can't even dream of. Thank you.